So this brings us to the topic of ensemble methods. So ensemble methods are a very powerful machine learning technique which are ranked right next to deep learning. This is used only when, let's say, when one particular algorithm is really difficult to choose, or it is being really difficult to train on, or to find, or to reduce the error, or to find the correct output. What we do is we group such models together in order to get the output that we require and to reduce the variance and the bias, right? One really good example and one very famous example of ensemble methods would be regression, uh, random forests, right? Because random forests are made up of decision trees, and as we learned that decision trees are highly unstable algorithm. So what we do is we combine different trees to create a forest, which we call a random forest, right? Another example would be Boost. So what does ensemble method do? Basically, it aggregates information into groups which are, let's say, one information that is of one kind. They are grouped in a group, and then uh, those groups are then used to train another model through which you get your output, right? You aggregate your estimates, your independent estimates, through weighted and your unweighted average, right? Let's say in a random forest, each decision tree is associated with a weight, with a particular weight. That weight defines the output that the random forest gives. So when we're talking about aggregating independent estimates, we say there are two ways. Let's write aggregating independent estimates, right? This can be done by two ways. Number one is weighted average, right? And the other one would be unweighted average, right? So this is basically committee of experts where if a particular classifier or a particular model is working really well on the set of data, we assign it more weight, through which it basically dictates the output that your ensemble method gives, right? So this is committee of experts. And if we're using unweighted average, we use the majority voting, right? Uh, so by with majority voting, I mean, like in the random forest, let's say there are 50 decision trees, right? Out of these 50 decision trees, 30 say yes for a class and 20 say no. So if you're using unweighted average, we'll use majority voting, right? So yes has more number of votes, therefore the output of the random forest would be yes, right? So these are like few of the ways how your ensemble methods work. So okay, when we're talking about weighted averaging, right? So in weighted averaging, what we do is we decrease the weight of correlated learners, right? Because let's say out of those 50 learners, right, 10 of the learners are uh, outputting the same thing, or basically behaving the same way. The models are behaving the same way on the set of data that they are given, right? What we do is we reduce the weight, because only the data from one of the models is enough to represent the data of 10 of them, right? So we don't need them. So we reduce the number, the weight associated with them, and we increase the weight of our good learners, right? Good learners are those which are able to basically catch your outliers or catch the points which other models are not able to predict or catch on, right? So those are our good learners. On the good learners, we increase the weights. So we treat the output of each model as a feature to train a new model, right? And in the mixture of experts, each weight is associated with alpha I, right? So this brings us to the next topic of ensemble methods, that is basically bagging. This is basically one of the simplest way of combining our predictions, right? So bagging stands for bootstrap aggregation, right? So you get B and the ag, so you get bagging, right? So bagging is basically a resampling technique which uses voting or averaging. right? So initially each of your model receives equal weight. So when your models receive equal weight, what you do is you sample several training sets of size, and then what you do is you train your classifiers with the weights associated with them, but with only the portion of the data that you sampled, right? And then you aggregate the output of each of those samples along with the weights that are associated with them, right? And you get the output of your model, the bagging model. So, right, you might have a question that, okay, if we're using 50 decision trees and we have just a one single database, how would the decision trees output different results, right? To tackle that, what we do is we create a random subset of data by sampling with replacements from the original data set, right? By doing so, we create a sample size of n instances by selecting n times, right? This becomes our new data set, right? So this new data set might contain some duplicates, some of the groups that we picked randomly might not contain duplicates, right? So those sets which do not contains duplicates, those sets consist of our test set. Those make up our test set, right? So right, these n instances, because we need for n models, right? The for ensemble methods, we are putting together n models together to reduce our variance and bias, right? So what we do is we pick n instances n times randomly from a data set, creating a new data set for each of our models. That is how we get a different behavior of our models on the same data set, and later on we aggregate all of that behavior to give out a final result, right? So this bagging method is applied on the collection of low bias and high variance models, right? So when we average over them, so what happens is our bias reduces but variance remains the same. So basically what we're doing is from a high variance low bias, that is the overfitting case, right? High variance and low bias, right? This is the case of overfitting. So if a model is overfitting, try and bag that model, right? By doing so, you'll be able to reduce the bias, but variance would remain the same because the variance happens to be on the data set, right? So bagging would 100, like in most of the times, it would reduce the bias by a lot, right? So let's discuss some pros and cons of our um, bagging model, right? So pros would be that it reduces overfitting, right? Because we were using it on a model having low bias and high variance, and obviously it generalizes better, right? For every good thing, there is got to be a bad thing associated with it, right? So the cons are that when a model is bagged, the structure of the model is lost, right? Because initially, if we are bagging a decision tree, so a tree becomes a forest. So the model of the structure of the model is lost, right? Um, and as we know that this is used on unstable algorithms mostly, so stable algorithms are not affected by it, right? So if there is lots of data and we learn some classifiers, right? So they'll have a lot of different outputs. So those different outputs, if we average them, the output does not help us too much, or like it is not what we want, right? So these are some pros and cons for our bagging method. So if we want to overcome these, what we do is there is a solution for it, right? So the solution is basically introducing extra variability and extra randomness in the procedure, right? So how do we do? So the solution for this would be, I would say that we use a subset of features even in the subset of the data set, right? So for every model, use subset of features, right? So this would introduce some sort of randomness in the type of data each model sees individually, right? And the other thing would be Once a model sees these subset of features and their output is given, now take the averaging or majority voting, right? So this introduces the randomness that we need to overcome the cons that are there, right? So this brings us to random forest. So an ensemble tree with random subset of features is called random forest, right? So that is how your decision trees are converted into random forests. So see, building a random forest, it's pretty simple. You just need to follow these 4 steps that are, one second, right. So these steps are: number 1, you randomly select n samples out of the database. So step 1 is random selection, right. So that brings us to step 2. Now we have to do is select a subset of features. So you select subset of features. Right, after you've done selecting the subset of features, you get to step 3. Then you build a tree on these features, and that too without pruning. Without pruning, right? Using these selected features. So step 4 would be repeat d times. That is the number of trees that you want in the forest. Okay. So now for every new sample, right, now once you've done these 4 steps, you've built your random forest. Now for every new sample, what you need to do is you need to predict the output using all of the trees inside the random forest and take the average or majority voting, right? So there might be like n number of trees like this in the forest, right? D number of trees, I'm sorry, because we have repeated d times. So what you do is, once you get a new sample, you run the sample through all of these trees, right? And then you aggregate it, or through majority voting, you aggregate the results, right? So now one interesting thing is, when you combine multiple linear classifiers in an ensemble, uh, so that gives us a non-linear classifier. So an ensemble linear classifier gives us a non-linear classifier, right? Okay. So now that brings us to the next topic of boosting. Okay. So boosting is a method with which we combine the weak learners together to form a very complex model, which can be used to predict even non-linear boundaries, right? So what are the properties of boosting? The properties are that it uses weak learners, right? What it does is, it starts training the learners one by one, right? So what happens is, like, once you train the first learner, you will find out, okay, it's misclassifying on certain examples, or it is misclassifying certain data points, right? So the new learner basically focuses on the mistakes of the old learner, right? The points that were misclassified, those are given a weighted priority or a higher weight, and the new learner basically focuses on the those examples which were classified wrong, right? At the end, what we do is, once all these weak learners are trained, we combine all the learners at the end, right? So if we take examples of weak learners, so weak learners would be um, decision stumps. These are basically decision trees with one node. Okay. Then naive Bayes model. Naive Bayes model is a weak learner. Perceptron is also another weak learner, right? So you see, if you take a single perceptron, it's very weak, right? But you combine multiple perceptrons together, you get a neural network, which is a very complex model, right? And it can predict nonlinear boundaries as well. So what we can say is, neural nets is a boosted version of perceptron, right? So now that brings us to Adaboost or Adaboost. Or before we discuss Adaboost, let's see how do we assign the weights and everything, right? So what we do is in the training set, we start off with the same weight for all the instances, right? As soon as an instance is misclassified, we give it a higher weight, right? So due to this, the next classifier is more likely to get this wrong classified example correct, right? So once it's correctly classified, you lose the weight or you decrease the weight, right? So I'll write down the steps, right? So boosting can be done in two ways, right? Where we learn with reweighted training set, and one where we learn with just weighted training set, right? So in learning with reweighted training set, what we do is we start off with some weight for all instances, right? Like every data point in your data set is given a certain weight, right? Now, misclassified examples gain higher weight as soon as it's misclassified. Certain value is added to its weight so that the weight value increases, right? So this is done so that the next classifier is more likely to classify correctly, right? Now, once a data sample is correctly classified, it loses its weight, right? So this is how you learn with reweighted set. Now, learning with weighted set where you don't change the weight for the instances, what you do is you just give different weights to loss function for different examples, right? As soon as it's misclassified, that weight is applied to the loss function, and the model works on the higher weights, right? Because those are the things that are affecting the loss function. Right now, what we do is we create a new data collection with multiple copies of samples with higher weight, right? So let's say every time we pick n samples out of the data set, random samples that we take, we include this data collection or this data with the high weights, right? So as every classifier can see them once and are able to classify them correctly at least, right? If they're able to correctly classify the wrongly classified sample correctly, then your whole model is able to correctly classify it, right? So this is how you train with weighted set. Okay, so now let's see the next topic of Adaboost, that is also called adaptive boosting, right? So what does adaptive boosting does? It uses stump trees, right? So stump trees are nothing but having one node and two leaves, right? So these are very weak learners. So as we are talking about boosting, we are talking about weak learners and combining weak learners together to form a complex learner, right? So what it does is it creates a forest of these stumps, right? Now this forest is created sequentially, a step by step, right? So you create one stump, the misclassification is carried forward to the next stump, and that's how you keep creating a forest, right? So it's sequential, right? Error at each stump affects the error at or affects the training data weights for the next stump, right? Error at each stump affects the training data weight for next stump, right? Because if it's misclassified, we have to increase the weight, but if it's classified correctly, we need to reduce the weight or lose its weight, right? So depending on the performance, each stump is given a different weight. Now this weight is a different weight. Till now, we're talking about weights associated with each data sample, right? So let's say this is x1, x2, x3, x4. So these are our data samples and we have weights associated with each of them, right? Now, each of the stumps are again associated with another weight that is given as lambda I. Now, lambda I, basically this depending on the performance of each stump, right? We assign a lambda I, which basically influences our final classification decision, right? Because this lambda I denotes the importance of each stump in the forest. Now let's look at the algorithm for it. So now we discussed the algorithm of boosting or Adabboosting, right? It's very simple, it's very straightforward, right? Now let's take a look. Okay, So our algorithm is boosting, where there are three inputs. That is the data set, the size of the ensemble, and the learning algorithm that is given by A. Right. The input is the given data set D, and the output is the weighted ensemble of models, which basically gives you the final classification result of your models. Right. So the first step would be to initialize the weights for all the instances. Let's say there are mod D number of instances in our data set. So each of them is given equal weights, right? Now for each ensemble, we learn the model, that is, let's say this is AJ, and this is the prediction, that is the Y hat I, right? So this is nothing but, this would be 0, right? This would be 0 if it is correctly classified, but if it's misclassified, it would be equal to 1, hence leading to the addition of the misclassified examples weight, right? So this term is nothing but weight of all misclassified examples upon total weight for a particular learning algo or a model, right? Once you have your epsilon j, using this epsilon j, you calculate lambda j. This is simple half of logarithm with base e, 1 minus epsilon upon epsilon. You get the value of lambda j. Now, what you do is, for each misclassified example, right? For each misclassified example, what you do is you multiply the weight with e to the power lambda j. But if it's correctly classified, this is misclassified, and this is correctly classified, right? So as we learned that every misclassified sample has to have their weight increased, and every correctly classified sample have to have their weight decreased, right? So we divide by lambda j to get a reduced weight for the next iteration or the next model, right? So this is how you proceed with the boosting algorithm. Now let's take an example. Now, just before that, now the final prediction is made via, as we have calculated our lambda I for each model into the model j with x, right? So this is the final prediction that you get. Okay. Okay, so now let's take an example for Adaboost. Okay, so we start off with this table, right, where you have blood pressure, weight, age, and whether that patient has a heart disease or not. Okay, so let's try out our algorithm that we just discussed. So the first step was to assign every one of them equal weights. So there are like 7 samples, 1, 2, 3, 4, 5, 6, 7. So each of them would be given a weight of 1 by 7, right? So we initially give every one of them equal weights. Now, let's say we want to build a random forest with, let's say, k trees, decision stubs. So, okay, now let's start. Now let's start building a decision stub. Let's say we start off with blood pressure. Okay. So blood pressure has 2 features, yes and no, right? So as you see, there are 4 samples for yes, 1, 2, 3, and 4, and there are 3 samples for no, right? And if you see the associated disease, if there is disease present or not, you would see that for the first, second, and the last yes, if the blood pressure is high, the disease exists, right? But in one of the cases, that is this case, you see the blood pressure is high, but still there is no disease, right? So this one sample would be misclassified, right? So you have 3 yes and 1 no, right? Similarly for no, you have 1, 2, 3 samples for no, out of which for this sample there is a misclassification, right? So there is 1 yes and 2 no's, right? When the disease is not present, the blood pressure is low, disease is not present. When the blood pressure is high, in this case, you see disease is not present, and similarly the blood pressure is not high but the disease is present. So if we go on to build a decision stub, these two samples would be misclassified, right? Now we proceed on to calculate our epsilon. What would be the epsilon? Epsilon would be, there are two samples out of 7 that are misclassified, right? So that gives us 2 by 7. Now using this 2 by 7, we can calculate our lambda j. That was half ln 1 minus epsilon upon epsilon, right? Calculating this, we get lambda j as 0.45, right? Once we have got our lambda j, for correctly classified samples, that are 5 samples out of 7, we give them the weights for correct. The weights are updated as current weight, that is 1 by 7 into e to the power 0.45, right? And for misclassified, that are these two samples, we give a new weight that is given as 1 by 7 into e to the power minus 0.45, right? My mistake, I'm so sorry. For correctly classified, we need to reduce the weight, right? So we take 1 by 7 into e to the power minus 0.45, whereas for misclassified samples, we need to increase the weight, right? So we multiply it with e to the power 0.45. This gives us the reduced weights as 0.09, whereas for misclassified samples, we get the weight as 0.22, right? So the new weights, that is for first stub. Now for second stub, the new weights for each of the data sample would be, for correctly classified, 0.09, 0.09, 0.09. For incorrectly classified, it would be 0.022, 0.22, 0.09 and 0.09, right? Now if you proceed on doing it again and again and again, you will see these will keep on reducing till the misclassified samples are correctly classified. Now this just has to be repeated the k number of times because we need k stubs in our random forest. One thing I forgot to mention, yes, that once we've got the weights, we need to normalize the weights as well, right? So the new normalized weights would be 0.09 upon 0.99 and 0.22 upon 0.99, right? This was simply calculated by taking the sum of all of the values that were given here. This is 0.99. So once you normalize, your new weights would be 0.1, 0.1, 0.1, 0.25, 0.25, 0.1 and 0.1, right? So these are your new weights after normalization. Now let's discuss some pros and cons for boosting. That would be our last topic, right? So as you see, the pros and cons are pretty much similar to what we discussed for bootstrap aggregation, right? So we don't need to use any complex models, right? Like basic models like perceptrons, decision stubs, naive Bayes can be used to convert them, group them together to create a very strong complex learner, right? It can boost performance of the weak learners, right? We have seen through decision stubs and through weighted averaging and all, you can increase the performance for good learners. It is very simple to implement. It's just you have to modify the weights for each data sample and keep using the same basic classifier that you have, the easiest classifier that you can have, and just keep using it, right? It decreases bias and variance. That is why probably we are discussing these models, right? And obviously it gives a good generalization. Now the cons are again pretty similar, that it loses that there is a lack of generalization. It loses its structural integrity as well, and it is very slow, not very slow, but it's comparatively slow during training and potentially during testing as well, right? So these are few of the pros and cons that are associated with Adaboost. So that pretty much completes our ensemble methods. I'll see you in next class. Thank you.